Welcome to this explainer. All right, let's just dive right into it. Today, we are demystifying something absolutely incredible: the field effect transistor, or FET for short. It is essentially the invisible backbone of our entire modern world. It's the tiny switch powering everything from the smartphones sitting in your pocket to the massive data centers running artificial intelligence. But honestly, this isn't just a story about shrinking technology. It's an epic saga of how scientists and engineers have relentlessly shattered the so-called impossible limits of physics. Here is a quick look at our roadmap for today. We'll kick things off with the switch that changed everything, then look at the CMOS power miracle. From there, we'll explore going 3D silicon skyscrapers before shrinking all the way down to the atomic flatlands. Finally, we'll leap into quantum leaps and AI brains, and then zoom back out to see how we are powering the macro world. All right, part one, the switch that changed everything. You know, every great technology has an origin story, and the transistor's history is basically a massive underdog story. The concept of the FET was actually patented way back in 1925 by a guy named Julius Edgar Lilienfeld, but for decades it was literally impossible to build because of these unpredictable physical barriers on the material's surface. Fast forward to 1959 at Bell Labs, where Martin Attala and Dawon Kong finally invent the MOSFET by figuring out how to passivate the silicon surface with an oxide layer. But here is the crazy part: Bell Labs initially ignored it. Why? Well, because the early MOSFET was about 100 times slower than the dominant heavyweight of the time, the bipolar junction transistor. Yet, by 1964 we had commercial chips, and by 67 the invention of the floating gate set the absolute foundation for the flash memory you still use today. So how exactly did the underdog win? It all boils down to one crucial physics quirk. Bipolar junction transistors, or BJTs, suffer from a fatal flaw when you pack them into dense circuits: a negative temperature coefficient. Basically, as they heat up, their resistance drops. They draw more current, generate even more heat, and eventually just destroy themselves in a vicious cycle called thermal runaway. FETs, on the flip side, are brilliantly self-regulating. As their temperature rises, electron scattering goes up, which naturally chokes off the current. That built-in thermal stability is the exact reason why we can cram billions of them onto a microchip, and your modern phone doesn't just melt right in your hands. Moving on to part two, the CMOS power miracle. Beating the heat was step one, but to build modern microprocessors, engineers had to tackle a massive power consumption problem. And the magic number here? 0. That is the ideal static power consumption of a modern digital logic circuit. We actually pulled this off with CMOS, which is the foundational building block of our whole digital world. It works by pairing two opposite types of transistors in a push-pull system: a PMOS, handling positive charge, and an NMOS, handling negative charge. When the circuit is just sitting there holding a state, what we call standby, one of those transistors is always completely 100% turned off. It physically severs the direct current path from the power source to the ground. That zero current standby is the absolute miracle that makes battery-powered mobile devices and massive memory banks a reality. Section 3. Going 3D Silicon Skyscrapers. For decades, the game plan was simple: just make flat transistors smaller. But eventually, physics fought back. I'm sure you've heard of Moore's Law, the idea that transistor density doubles every 2 years. Well, as we pushed flat transistors past the 20-nanometer mark, we hit a massive physical roadblock. The source and the drain got so close together that the gate couldn't control the flow of electrons anymore. They just started leaking everywhere, a huge headache known as short channel effects. To save Moore's Law, engineers couldn't just build outward anymore. They had to build upward. This whole architectural evolution is exactly like building a city of skyscrapers. First up, we got the FinFET. The silicon channel stands up like a little shark fin, which lets the gate wrap around 3 sides to pinch off those leaks. But as we push below 5 nanometers, even that wasn't enough. So enter step 2, GAAFETs, or nanosheets. We slice the channel into flat sheets and wrap the gate completely around all 4 sides for perfect control. Step 3 is the fork sheet, which squeezes the N and P-type transistors incredibly close together using a microscopic insulating barrier, a dielectric wall. And finally, step 4, the absolute pinnacle of 3D evolution, the CFET. This literally stacks the NMOS directly on top of the PMOS vertically. Boom! You instantly cut the required footprint in half. But you know, even skyscrapers have height limits, which leads us to a pretty wild, provocative question. What on earth happens when silicon simply runs out of room? What happens when we push below 1 nanometer, where standard silicon is just too rough and electrons scatter helplessly? That brings us to Section 4, the atomic flatlands. To answer that question, scientists literally had to rethink the fundamental chemical fabric of the transistor itself. Let me introduce you to the savior of the sub-1 nanometer era. 2D transition metal dichalcogenides, or TMDs, like molybdenum disulfide. These materials are totally mind-blowing. You can peel them into single atomic layers just 0.7 nanometers thick. But their real superpower is that they form perfect, atomically flat surfaces with zero dangling bonds, meaning there are no broken chemical links on the surface. Because it's so flawlessly smooth, electrons just glide right through without scattering, even at this extreme atomic scale. Now, there is a catch. That perfection creates a major manufacturing dilemma. To actually build the transistor, we have to deposit a high-K dielectric layer, basically a super insulating cap, right on top of it. But standard manufacturing relies on those dangling chemical bonds for things to stick, so the dielectric just wouldn't adhere to the smooth 2D surface. It beat it up like water on a freshly waxed car. No way it was sticking. The solution? Pure brilliance. Researchers introduced an ultra-thin aluminum oxide seed layer. This layer gently coats the 2D surface and provides the absolute perfect chemical bridge for the rest of the transistor to be built on. Problem solved. Next up, Section 5, Quantum Leaps and AI Brains. As components get down to the size of atoms, we enter the wonderfully weird world of quantum mechanics. And instead of fighting it, engineers are now using it to their advantage. To understand this, we first have to understand the enemy here, the Boltzmann tyranny. It's a strict rule of classical physics dictated by thermal energy. It says that at room temperature, it takes at least 60 millivolts of gate voltage to increase the current by a factor of 10. For a long time, this seemingly unbreakable law completely blocked our chips from operating at ultra-low power levels. So, how exactly do you break an unbreakable law? You cheat with tunnel FETs, or T-FETs. Instead of using brute heat energy to push electrons over a physical barrier, T-FETs use a process called band-to-band tunneling. They essentially use the material's natural energy band gap as a quantum filter, and the electrons literally teleport through the barrier. By filtering out all the high-energy electrons, T-FETs effortlessly smash right through that 60 millivolt Boltzmann limit, dropping power consumption down to microscopic levels. And we aren't just reinventing how transistors switch, we're fundamentally changing how they think. Enter FETs, ferroelectric FETs. Traditional computing wastes a staggering amount of energy just shuttling data back and forth between the processor and the memory. FETs fix this by baking a special material called HCO directly into the transistor. This stuff actually remembers its electrical polarization even when you cut the power, so the transistor can store data and process logic at the exact same time. Even better, it can hold multi-level analog states, which perfectly mimics the synapses in a human brain. It is quite literally the hardware breakthrough we need for the next generation of highly efficient AI. Finally, let's scale way back up. Section 6, Powering the Macro World. We've spent a lot of time down in the quantum realm today, but FET technology also drives the massive power systems running our cell towers, cities, and electric vehicles. Standard silicon? It literally melts under the brute force of modern power demands. So we bring in the heavy hitters, wide bandgap devices. Two main champions are taking over the macro world right now. On one side, we have gallium nitride, or GaN. Its horizontal structure lets electrons move crazy fast, making it the undisputed king of high-frequency switching. It's the reason your modern fast chargers are so incredibly tiny, and it's the absolute backbone of 5G cell towers. On the flip side, we have silicon carbide, or SiC. SiC uses a vertical structure where massive currents just punch straight through the chip. It boasts extreme heat and voltage resistance, making it the absolute gold standard for the heavy lifting required in EV inverters and solar grids. They aren't competing at all, they're just conquering completely different domains. As we wrap up this explainer, I really want you to leave with this thought. The evolution of the FET is not just linear scaling, but a relentless breaking of the physical limits of computing and energy. From a rough sketch in the 1920s to quantum teleportation and brain-like AI circuits, the transistor has survived by constantly rewriting the laws of what is possible. So the ultimate question I'll leave you with is this. When we finally map every single atom and manipulate every quantum state, what impossible limit will human ingenuity shatter next? Thanks for learning with me today, and keep exploring.